All right, welcome to this explainer. Today, I'll be stepping in as your senior technical strategy consultant. Look, if you're an automotive R&D leader or a professional engineer trying to navigate the absolute maze of our industry's future, you are definitely in the right place. We're going to decode the specific engineering pathways laid out in the highly anticipated China Energy Saving and NEV Technology Roadmap 3.0. And we're going to deconstruct these pathways to the 2040 carbon neutrality goals using a rigorous, McKinsey-style top-down strategic framework. Okay, let's dive right in. To tackle a roadmap this vast, we'll use a mutually exclusive, collectively exhaustive, or MISI framework. We'll quickly run through the 2040 strategic architecture, high-efficiency powertrain limits, zero-carbon engine evolution, the automotive lightweighting trinity, systemic vehicle energy saving, and finally, ecosystem synthesis.
Let's kick things off with Section 1, the 2040 strategic architecture.
So right now, we are confronting what's known as the efficiency paradox. Check this out. A-class EV energy consumption actually dropped beautifully to 12.24 kilowatt hours per 100 kilometers back in 2021. But by 2024, it crept back up to 12.49. Why is that happening? Well, it's because the massive weight of larger batteries and these heavy, intelligent domain controllers is basically like carrying a phantom passenger in the car at all times. It's just eating up our efficiency gains. Plateauing EV efficiency means we need a total paradigm shift. We can't just optimize isolated components anymore. We absolutely need a systemic dual driver, extreme hardware innovation perfectly paired with software intelligence. When we look at the macro timeline, we have to shatter the pure EV-only myth right here and now. Internal combustion is not dead, folks. It's just evolving. By 2040, traditional passenger vehicles are going to see 100% hybridization. On top of that, zero-carbon engines will hit a 15% commercial penetration, and all of this is going to be fused together by an AI-driven V2X ecosystem. We are living in a multi-path reality.
Moving right along to Section 2, high-efficiency powertrain limits.
The bottom line engineering objective we're looking at here is incredibly aggressive. For hybrid and plug-in hybrid dedicated engines, the target is 48% peak thermal efficiency by 2040. For range extenders, we are literally pushing beyond the 50% physical limit. And heavy commercial diesel, 55% or greater. That is huge. The ultimate goal is to keep the brake-specific fuel consumption, the BSFC, locked right in the optimal economic zone across almost all operating conditions. What this strategic shift really tells us is that EVs and ultra-high-efficiency hybrid architectures are going to coexist for a long time. For passenger vehicles, our engineers need to completely master multi-gear dedicated hybrid transmissions. We're talking about combining 2-speed or 3-speed gear sets with dual motors, which is absolutely crucial to guarantee global energy security and keep the grid stable. Now, to shatter those thermodynamic boundaries, we have to deploy some truly aggressive enablers. We're talking about 500-bar direct fuel injection systems just to achieve micron-level atomization. We need geometric compression ratios pushing past 15:1, and to manage the severe knock limits and that pesky early ignition at those extreme pressures, we have to utilize deep, low-pressure EGR. We're essentially pushing exhaust gas recirculation rates up to 30% just to cool the combustion chamber and suppress NOx formation. It's intense engineering.
Let's shift gears to Section 3, zero-carbon engine evolution.
If we're really shifting to zero-carbon fuels, the absolute game-changer here is HPDI, or high-pressure direct injection. This is a breakthrough technology that we absolutely must have to overcome the exceptionally slow flame propagation speeds of alternative fuels. Basically, you inject a tiny amount of a high-reactivity pilot fuel, like diesel, to act as a sort of liquid spark plug. It auto-ignites, creating these high-temperature jets that reliably ignite your main zero-carbon fuel, whether that's ammonia or methanol. Now, hydrogen and ammonia present some incredibly distinct, tricky engineering challenges. Hydrogen demands ultra-lean diffusion to overcome its super-low ignition energy. If you don't get that right, you're looking at severe pre-ignition and backfires, not to mention having to use specialized alloys to stop hydrogen embrittlement. Ammonia, on the flip side, requires us to master the stable combustion of a very low reactivity fuel. Oh, and you have to strictly manage toxic, unburned ammonia slip and N2O emissions. Not an easy task, right?
The evolution path for these zero-carbon engines is actually incredibly clear, and it's moving fast. Phase 1 is mastering port fuel injection, but by 2040, The ultimate limit will be achieved by combining that HPDI technology with stratified ultra-lean combustion and seamlessly integrating liquid hydrogen storage directly into the commercial vehicle chassis.
All right, Section 4, the automotive lightweighting trinity. R&D leaders are facing a massive weight paradox right now. Think about it. Batteries give us range, but their mass takes it right back. Aggressive mass reduction is absolutely no longer just a nice little cost-saving measure. It's a foundational, non-negotiable physical requirement if we want to preserve dynamic range, handling, and commercial payload capacity. So, how do we solve this? The roadmap prescribes what we call a trinity approach. Structurally, we're shifting away from isolated components toward holistic cell-to-chassis, or CTC architectures, where the battery case itself actually provides the core torsional rigidity. Process-wise, we're using high-yield gigacasting to replace hundreds of individual stampings with single aluminum nodes. And tying the whole shebang together, AI-driven generative design that mathematically strips out literally every single gram of unnecessary material. When we look at the future body in white, we are targeting a massive 30% reduction in the lightweighting coefficient for passenger EVs by 2040. To hit that, we're applying 2,500 megapascal hot stamp steel for the safety rings. At the same time, we're integrating novel basalt fiber reinforced plastics alongside continuous carbon fiber matrices to get these absolutely extreme strength-to-weight ratios in our battery enclosures. Let's move to Section 5, Systemic Vehicle Energy Saving. We have to sequentially attack every single parasitic loss across the entire vehicle envelope. And honestly, the 2040 targets are staggering. We are aggressively pushing aerodynamic drag coefficients down to 0.17 or even lower. We have to integrate ultra-low friction hub bearings and zero-drag brake calipers that have a drag torque of less than 1.5 newton meters. And fundamentally, we've got to completely rethink thermal management to finally stop that awful cold weather range degradation. The industry is rapidly abandoning those old, fragmented, discrete cooling loops. Instead, we're moving toward highly integrated, AI-driven, wide-temperature heat pumps. By using multi-way valves like an octavalve and eco-friendly refrigerants, the system dynamically scavenges low-grade waste heat from the powertrain and actively routes it to the cabin or the battery. This is exactly how we're going to push cold-weather AC power draw well below 1,400 watts. And finally, Section 6, Ecosystem Synthesis Imperatives. Look, hardware optimization eventually hits a physical ceiling, right? But think of the 2040 paradigm like an infinity loop. The first three pillars we discussed, powertrains, zero-carbon engines, and lightweighting, they establish the absolute physical capability limits of the chassis. But then, the Vehicle Road Cloud, or V2X software, steps in as the ultimate multiplier. It dynamically extracts maximum utility from that hardware by predicting traffic, optimizing routes, and managing thermal loads in real time. It's brilliant. Consequently, R&D leaders, you have to pivot. You have to shift your focus from isolated component efficiency over to domain-fused AI platforms. You've got to aggressively invest in multipath infrastructure because pure EV is simply not the sole endgame. And crucially, you have to master the hardest engineering challenges found right in the seams. Things like joining dissimilar materials, say cast aluminum to ultra-high-strength steel, without causing galvanic corrosion. That is where the real battle is won. Let's wrap this up. As energy saving transforms from a localized, mechanical task into this massively interconnected digital and physical ecosystem, I want to leave you with this final thought. Hardware sets the baseline, for sure, but software is the multiplier. So, are your engineering architectures truly prepared for the 2040 realities? Thank you so much for joining me on this explainer. Keep innovating out there, and I'll catch you next time.
Hey everyone, let's jump right in. As a technical strategy consultant working with top-tier automotive firms, my job is to figure out exactly where this industry is heading. So today, we're doing a deep dive explainer on the China Energy Saving and New Energy Vehicle Technology Roadmap 3.0. We're zeroing in entirely on the application trends and that macro engineering blueprint for the 2040 mobility ecosystem. If you're out there designing tomorrow's platforms, this is the top-down playbook you absolutely need to master.
Look, to really grasp this 2040 paradigm shift, we've got to zoom way out. For years, we've all been optimizing isolated components just to shave off a little energy consumption per 100 kilometers, right? But looking at this new engineering schematic, it's a whole new ballgame. The optimization problem isn't just about efficiency anymore. It's about full lifecycle carbon footprint minimization across the entire value chain.
To tackle something this massive, we're going to apply a strict MISI framework, mutually exclusive, collectively exhaustive. We'll hit 4 specific pillars: power batteries, fuel cells, e-drive systems, and infrastructure. And then we'll tie it all together by looking at the ultimate 2040 ecosystem convergence.
This matrix is basically your blueprint. It visually drives home the point that achieving market leadership in 2040 relies entirely on mastering the combinatorial effects of these 4 interconnected gears. You can't just win at battery chemistry and drop the ball on grid integration. The zero-carbon transport matrix demands simultaneous mastery across the board.
All right, let's start with Pillar 1, power batteries. This is where the strategic mandate forces us into a really fascinating dual-track paradigm. The divergence here is just stark. The industry isn't chasing one single, unified goal anymore. On one track, we're pushing solid-state chemistry to its absolute physical limits. We're talking energy densities well over 700 watt-hours per kilogram. But on the flip side, on the cost-effectiveness track, the mandate is to ruthlessly crush costs down to under 0.30 RMB per watt-hour by hyper-optimizing liquid lithium-ion systems. It really makes you stop and ask, where exactly does your current R&D pipeline fit into this split?
Now, tracking that high-density route requires a highly specific, multi-step material evolution. We're stepping away from today's liquid NCM and graphite setups, moving into a semi-solid integration phase that relies heavily on lithium-rich manganese and high-capacity silicon carbon anodes. And then, finally, by 2040, we fully cross the threshold into all solid-state systems utilizing pure lithium metal.
In this timeline, it's dictated purely by material physics. For example, hitting an ionic conductivity above 2.0 times 10 to the negative second Siemens per centimeter for sulfide-based solid electrolytes is literally the physical gateway. If we don't hit that exact material metric, those 2040 solid-state targets remain nothing more than a theoretical fantasy.
Switching gears to the high cost-effectiveness track, it's not really about chemistry. It's all about extreme packaging and next-level manufacturing. We're aiming for 90% mass and volume grouping efficiency through pure cell-to-chassis integration. And to hit that staggering 0.04 RMB per watt-hour manufacturing cost, you've got to rely on fully automated dark factories. We're talking lights-out operations, blazing fast speeds, and a 99.99% pass rate.
Moving on to Pillar 2, fuel cells. The roadmap is crystal clear here. This is our endgame specifically for heavy-duty commercial decarbonization. Hydrogen isn't some blanket fix. We are isolating it for those brutal, continuous operation logistics corridors, where heavy batteries would totally kill your payload capacity. For a 49-ton heavy-duty truck, the 2040 targets are wild. Over 4 million operational fuel cell vehicles, minimum 1,000-kilometer ranges, and pushing their ability to a 2 million-kilometer lifespan. Oh, and keeping hydrogen consumption strictly under 6 kilograms per 100 kilometers. To actually pull that off commercially, engineering teams have to crack the platinum bottleneck right at the membrane electrode assembly level. The mandate is a microscopic cathode platinum loading limit of 0.12 milligrams per square centimeter by 2040. To hit that, we're going to need massive advancements in high-temperature proton exchange membranes and totally stable non-platinum catalysts.
Let's tackle Pillar 3, e-drive systems. Here, we are witnessing a radical shift from standard mechanical packaging to pure silicon-level hyper-integration.
Those legacy decentralized powertrains, they are officially dead. The future is entirely unified, multi-in-one domain control units. We're treating e-drives as silicon-level computational actuators now. By leveraging multi-core microprocessors and wide bandgap semiconductors like silicon carbide, we're targeting a volumetric power density of 70 kilowatts per liter by 2040. It's honestly just like the leap we saw in computing decades ago, going from mechanical sprawl to incredible processing density. Mechanically, this translates beautifully into distributed drive engineering. We are pushing toward wheelside and hub motor architectures with mass torque densities beyond 27 Newton-meters per kilogram. This fully decouples the chassis dynamics, letting us seamlessly drop in by-wire steering and braking. Imagine the freedom this gives us. We can completely revolutionize vehicle handling and massively open up the interior cabin.
Our fourth and final standalone pillar is infrastructure. Get ready for the VTG revolution, where we stop treating EVs as a burden on the grid and start treating them as highly profitable assets.
By 2040, we're looking at a very distinct dual-track energy network. On one hand, we're building massive hydrogen logistics corridors, deploying up to 20,000 targeted stations for heavy transport. Concurrently, in urban environments, we are transforming standard charging piles into smart, bidirectional nodes. We are basically turning city grids into massive virtual power plants.
The aggressive scaling mandate here is what you really need to take note of.
Hitting over 80% vehicle-to-grid or V2G penetration by 2040 means fleets will automatically absorb off-peak renewable energy and shave those peak grid loads when demand spikes. Your vehicles literally become prosumers, producing and consuming energy on the fly. They aren't just getting you from point A to B anymore, they're rolling power utility nodes.
So having verified the requirements across all 4 pillars independently, let's move to our final section, synthesizing them into the 2040 ecosystem convergence.
It's glaringly obvious that the 2040 market is going to belong exclusively to whoever masters this exact convergence. The ultimate vehicle is no longer a hardware product, it's a software-defined node that seamlessly interlocks smart solid-state batteries, fuel cell networks, computational e-drives, and V2G infrastructure. Unifying that entire shebang with AI and digital twins, that is how we actually minimize the lifecycle carbon footprint at a macro scale.
As we wrap up this explainer, I want to leave you with a critical question to take back to your teams. Take a hard look at your organization's R&D pipelines right now. Are they still structured just to win at isolated components? Or are you genuinely engineering for this massive, systemic 2040 ecosystem convergence? The jump from market follower to global architect really depends on how you answer that. Thanks for tuning into this explainer, and let's keep building the future.
Welcome. Let's get right into our strategic deconstruction of China's Intelligent Connected Vehicle Technology Roadmap 3.0. As a technical strategy consultant, I review a lot of industry white papers. But for those of us deeply embedded in automotive engineering, this one hits entirely different. It's not just a high-level policy update. It is a definitive, quantitative, hard numbers blueprint. We're going to look at the fundamental transition from the traditional, isolated vehicle logic we all grew up with straight toward a fully integrated global ecosystem. Take a look at the overarching strategic shift happening here. We are completely migrating away from the standalone autonomous vehicle, that traditional single-node approach, toward a fully AI-driven, zero-accident vehicle road cloud, or VRC architecture. Honestly, this is a total paradigm shift for our industry. It literally redefines the boundaries of mobility, suggesting that the ultimate product is no longer just the car sitting in the driveway, but the entire interconnected network it breathes in. To unpack this complex 2040 blueprint, we'll use a top-down MEC framework, mutually exclusive, collectively exhaustive. We're going to hit 5 core areas: the VRC integration framework, edge execution, network and cloud control systems, infrastructure and converged safety, and we'll wrap up with the strategic engineering imperatives. All right, starting right at the top, Section 1, the VRC integration framework. At the absolute apex of this vision, we have to contrast our legacy architecture with this new future mandate. Look, as engineers, we intimately know the limits of those legacy module-based, rule-driven silos. They are inherently brittle, right? When you force them to handle infinite, unpredictable, long-tail corner cases on open roads, they just break down. The Roadmap 3.0 mandate draws a massive line in the sand. If we want to scale true, reliable autonomy, we have to abandon single-vehicle intelligence. It's all about data-driven, end-to-end AI and absolute systemic network capability now. And here is why that shift is absolutely crucial. Right now, our industry faces a major structural risk. We've got upper-layer prosperity resting on a really brittle foundation. Just look at the market today. We're seeing massive prosperity in user interface innovations, unbelievable deployment scale, and rich app ecosystems. But all of that success is resting dangerously on a heavy reliance on foreign high-compute chips, non-indigenous operating systems, and imported testing toolchains. The roadmap basically demands a radical R&D pivot toward indigenous full-stack development to lock down and secure this digital base. So how do we solve this structural risk? The roadmap mandates a strict MEC architecture, dividing the entire engineering domain into 6 mutually exclusive but collectively exhaustive pillars. We've got intelligent driving, the intelligent cockpit, connected collaboration, the cloud control platform, intelligent infrastructure, and connected safety. Together, these 6 perfectly exhaust the technical boundaries of this ultimate VRC organism. Moving right along to Section 2, Edge Execution, focusing on driving and the cockpit. When you track the engineering progression from 2030 to 2040, you see an incredibly aggressive acceleration timeline. By 2030, L2+ essentially becomes the absolute baseline standard across new vehicles, right alongside some crucial breakthroughs in L4 tech. Fast forward just 5 years to 2035, and we're looking at L4 autonomous operations scaling into the millions. And by 2040, We definitively crossed the technology chasm. L4 becomes fully ubiquitous, and L5 systems actually make their commercial market entry. Diving into Pillar 1, the engineering paradigm for intelligent driving is shifting radically. I mean, we are literally replacing hundreds of thousands of lines of modular C++ code with input-to-output neural networks mapped dynamically right in latent space. This end-to-end AI revolution relies heavily on massive data closed loops to solve those tricky edge cases. And get this, the target KPI is less than one takeover per 10,000 kilometers by 2040. That is absolutely staggering. For Pillar 2, the intelligent cockpit is evolving way beyond a simple infotainment display. It's becoming a comprehensive cognitive space, basically a third living space. For you systems architects out there, the compute demands are going to be massive. We're talking about crossing the 1,000 TOPS threshold of edge compute. But more importantly, it requires deep hardware hypervisors to strictly isolate safety-critical ASIL-B driving tasks from your everyday QM entertainment tasks on the exact same system on chip. It's all about delivering a seamless, proactive experience without compromising functional safety for a second. Next up, Section 3, Network and Cloud Control Systems. Look, a standalone vehicle always has a hard physics limitation, sensor blind spots. To overcome these non-line-of-sight limitations, the strategic imperative here completely relies on ubiquitous, ultra-reliable, low-latency communication, or URLLC. By consistently hitting really stringent 10 to 20 millisecond latency targets, the network enables massive multi-agent computational scheduling and real-time AI model training loops. It essentially turns isolated vehicles into one giant collaborative swarm. And coordinating that swarm is the cloud control platform, which acts as the systemic brain of the entire operation. It utilizes highly decoupled architecture to handle wildly varying scales of processing. You've got the central cloud managing macroscopic traffic flow and foundation model training, while the regional and edge clouds drop down to handle ultra-low latency data aggregation and real-time vehicle control loops right at the street level. Let's pivot to Section 4, Infrastructure and Converged Safety. Here, we're seeing a truly fascinating convergence of hardware and software. The concept of light map plus heavy perception digitizes the physical world using smart roads and multi-sensor fusion. Meanwhile, over on the security front, we're completely abandoning fragmented safety protocols. Instead, we're moving to a 4-in-1 converged shield. This integrates traditional functional safety, SOTIF, that's safety of the intended functionality, and rigorous cybersecurity into one unified, holistic threat model. To really grasp this integrated protection, we have to stop viewing this roadmap as just a collection of automotive parts. It is a deeply intertwined cyber-physical system. Think of it as a closed-loop engineering organism, where computational algorithms, high-speed VDX networking, and physical roadside infrastructure must operate in absolute concert to execute multi-dimensional traffic control safely. Which brings us to our final core area, Section 5, Strategic Engineering Imperatives 2040. As engineers, we respect data above all else, right? Well, this execution matrix clinically details the harsh physics and compute realities required. Look closely at the safety column for 2040. The industry is targeting a 10 million kilometer mean time between failures, or MTBF, for systemic safety. Let that sink in. Those are uncompromising, rigorous targets that will entirely redefine how we validate automotive systems going forward. To actually hit those rigorous KPIs, R&D teams must pivot entirely toward 4 interconnected strategic mandates. Number 1, overcome core tech bottlenecks by fixing that brittle foundation we talked about using indigenous full-stack development of chips and OS. Number 2, build robust data and AI flywheels utilizing synthetic data pipelines. Number 3, accelerate VRC commercialization by moving way beyond just pilot zones. And finally, strictly enforce system-level security validation across the entire network. Ultimately, our engineering focus has to shift aggressively. We absolutely have to move away from isolated, boutique pilot projects. R&D capital needs to be heavily allocated toward massive, low-cost, long-tail scenario simulation and virtual physical fusion testing. The traditional V model of systems engineering as we know it is basically being compressed and integrated directly into the cloud. So, as we wrap up this explainer, the definitive question for every senior engineer, product manager, and automotive architect out there is this. Is your current R&D pipeline truly prepared for the systemic network capability required by the 2040 mobility order? Can your current architecture survive the monumental shift from single vehicle intelligence to an entirely symbiotic, zero-accident VRC ecosystem? The blueprint is drawn. The engineering challenge is clear. Thanks for joining me to unpack it.
Welcome to The Explainer. I'm putting on my technical strategy consultant hat today because we are executing an elite, top-down strategic deconstruction of the China energy-saving and NEV technology roadmap 3.0. For all of us in vehicle engineering, this isn't just theory. We're zeroing in on the common supporting technology roadmap to analyze exactly what the mechanical and digital architecture of our industry is going to look like by 2040.
Here's our roadmap for this breakdown. First, the AI native ecosystem thesis. Then we'll slice the 2040 vehicle into 4 foundational pillars: intelligent chassis, EEI architecture, auto chips, and vehicle OS. Finally, we'll wrap up with the ecosystem imperative.
All right, Section 1, the AI native ecosystem thesis. We're moving way beyond isolated components into deep, system-wide integration. As an engineering community, we really have to internalize this massive paradigm shift. The era of the isolated, purely mechanical vehicle is officially dead. The new baseline for competitiveness doesn't come from tweaking a single brake caliper or optimizing one isolated ECU. It relies entirely on the deep cross-domain integration of the chassis, EEI, chips, and OS. That is an absolute necessity if we're going to hit the 2040 vision of an ecosystem that's genuinely low carbon, high efficiency, and zero casualty.
To really understand this, we're applying a strict MISI framework, mutually exclusive, collectively exhaustive. We can take the massive, highly complex 1 + 5 + 26 structure of the Roadmap 3.0 and cleanly distill it down into 4 interlocking layers. Think of the intelligent chassis as the execution layer. The EEI architecture is the central nervous system. Auto chips are the silicon synapses, and the vehicle OS is the conscious brain. Now here's the catch. A bottleneck in just one of these layers caps the performance of the entire vehicle ecosystem.
Let's dive into the first pillar. Section 2, the intelligent chassis, which acts as the physical decoupling and musculoskeletal execution layer. Tracking the morphological timeline, we're looking at a total departure from rigid mechanical linkages. By 2030, we'll have fully established the foundation for complete X-by-wire systems. And by 2040, we achieve standardized, service-oriented physical modules. We're talking about a complete decoupling of the upper and lower body. Imagine giving OEMs the freedom to mount a high-end luxury cabin or, say, an autonomous urban delivery pod onto the exact same self-adaptive skateboard chassis. That's the level of flexibility we're building toward.
But of course, the safety engineering challenge here is completely immense. Just look at the evolution of steer-by-wire redundancy. Right now, looking at 2025 standards for Level 3 autonomy, a 6-phase motor with basic circuit redundancy does the job. But fast forward to 2040, aiming for full Level 5 autonomy, and the entire paradigm shifts. It demands absolute fail operational capabilities. We are talking dual motors, totally independent control systems, and full physical and logical redundancy from top to bottom. It's a massive leap in engineering rigor.
Moving up the stack to Section 3, EEI, or the Electronic, Electrical, and Information Architecture, the central nervous system.
We're tracking a really radical evolution in topology. We're actively moving away from the legacy distributed ECU model, where a car was essentially a messy network of 100 isolated black box computers. We transition to a central compute and zonal architecture by 2030. And the endgame for 2040? A fully vehicle cloud centralized architecture where massive computational loads are handled entirely elastically in the cloud.
Now, why does this matter so much to us as engineering leaders? What's the bottom line? It's agility. By structurally decoupling the hardware and software lifecycles through a service-oriented architecture, we completely shatter legacy development limits. By 2040, these fully virtualized networks are going to compress feature development cycles down to just 1 week via AI-driven agile development. You are literally going to be updating a 2-ton kinetic machine with the exact same speed and ease as updating a smartphone app.
Which brings us to Section 4, auto chips. These are the exponential silicon synapses providing all the raw computational horsepower.
The gap between legacy chips we're used to and the 2040 requirements is honestly staggering. To support true in-car artificial general intelligence, we're demanding a compute threshold exceeding 2,000 TOPS. But as we all know, power means absolutely nothing without reliability. We are enforcing a strict zero-defect tolerance of less than 0.2 parts per million. Think about that. You are essentially engineering a world-class supercomputer and shoving it into a high-vibration, temperature-extreme oven.
Securing this kind of hardcore silicon ecosystem requires 3 absolute dependencies by 2040. Number 1, architecture autonomy. We have to establish open-source standards like RISC-V to break our reliance on proprietary instruction sets. Number 2, fabrication nodes. We need to master 22 to 16 nanometer embedded memory and advanced 3D packaging to get around the memory wall. And number 3, tool chain independence. We must completely transition to autonomous vehicle-grade EDA tool chains.
Next up, Section 5, the Vehicle OS. If those chips are the synapses, the OS is the conscious brain, bringing AI-native intelligence to the vehicle.
The performance metrics for a vehicle OS managing life and death execution are utterly unforgiving. It all comes down to deterministic latency. By 2040, the microkernel interrupt response time for ADAS control simply must be under 2 microseconds, end-to-end task delay capped at under 12 milliseconds, and it has to seamlessly orchestrate 2,000 teraflops of compute while maintaining absolute, uncompromising ASIL-D safety compliance. There is literally zero margin for error here.
Finally, Section 6, the ecosystem imperative. This is where cross-domain synergy dictates total system survival. We've deconstructed the 4 AIME-CE pillars, but the real magic, and frankly the real danger, lies in their interdependency. Let's walk through a critical scenario. Say a sudden mechanical failure requires a Level 5 autonomous vehicle to execute a redundancy switch. That entire digital cascade has to happen in under 1 millisecond. The OS microkernel processes the interrupt in under 2 microseconds. The chip instantly outputs 40K DMIPS. The EEI transmits the data via a 50 gigabyte per second network with 0 packet loss. Only then can the physical chassis actually execute the switch. The brutal engineering insight here? Missing a single target in any one of those layers collapses the entire safety architecture.
So how do we avoid getting caught in the fragmentation trap? There are 3 strategic imperatives. First, mandate core tech autonomy. Focus your R&D heavily on the choke points, like SILD MCUs. Second, champion open standards. It is time to abandon walled gardens and push for industry-wide baselines. And third, deploy advanced virtual validation. You need to invest heavily in model-based systems engineering and digital twins if you want to compress these complex development cycles.
I want to leave you with this final, somewhat provocative thought. You and your team might have engineered the absolute perfect brake module, or maybe the fastest edge processor on the market. But in this software-defined, highly integrated era, single-point solutions are destined to fail. Your specific component might be completely ready for 2040, but is your ecosystem? I really encourage you to think about that as you map out your next engineering cycle. Thanks for joining me on this explainer.
All right, let's get right into it. Welcome to today's explainer. I'll be stepping into the role of your senior technology strategy consultant today, bringing insights you'd expect from a top-tier global automotive engineering firm. We're going to do a deep dive into one of the most critical engineering frameworks of this decade, the China Energy Saving and New Energy Vehicle Technology Roadmap 3.0. Specifically, we're tearing down Part 5, the Intelligent Manufacturing Technology Roadmap. Look, the auto industry is at a massive historic pivot. We're totally moving away from just, chasing scale. Instead, we're entering a hyper-competitive global landscape completely defined by data, algorithms, and deep decarbonization. Consider this roadmap your absolute strategic blueprint for surviving and dominating that shift.
But to really grasp this blueprint, we have to completely radically shift our engineering mindset. Vehicles are no longer just static products rolling off a line. They are now self-optimizing nodes within what's called a neural factory ecosystem. The goal? To continuously iterate the new automobile. Think of the factory as an industrial mother machine, literally a living, breathing entity. It runs on a continuous, bidirectional flow of data. The factory builds the smart vehicle, and then, boom, the vehicle's real-world telemetry data flows right back to upgrade the factory. It's a flawless, closed, symbiotic loop.
And you can see exactly where this is heading with this maturity matrix. It all culminates in a massive 2040 mandate. 40% of the industry must reach an AI-driven, self-evolving state. They call this IM4. We're tracking the evolution from IM1, which is just basic digitization, all the way up to IM4. And get this, by 2040, a staggering 85% of the industry is expected to be operating at either the intelligent or fully self-evolving stages. Honestly, if your current manufacturing architecture is still just messing around with basic networking, you are already miles behind the strategic curve. So, to really operationalize this for you, we're going to break it down using a top-down MEAS approach. That's mutually exclusive, collectively exhaustive. We'll hit 1. Genesis and governance, 2. Physical realization,
3. Value network. 4. Market and sustainability. And finally, 5. Synthesis and strategy.
This radar right here, this is our cognitive map for today. We're splitting the entire ecosystem into the brain, the muscle, the nervous system, and the ultimate impact. And keep this in mind as we go. Competitive advantage today requires systemic superiority. A lag in any single node completely compromises the entire ecosystem. I mean, you literally cannot have IM4 level production equipment if your supply chain is still chugging along at IM2. The whole thing has to evolve synchronously.
Starting with Section 1, Genesis and Governance, the ecosystem brain. This covers digital R&D and digital management. It's where the genetic code of the new automobile is actually written.
And the big paradigm shift you need to grasp here is the pivot away from isolated physical prototyping. We're moving strictly to model-based systems engineering, MBSE, and AI-driven generative design. The old days of, throwing documents over the wall between mechanical, electrical, and software teams, yeah, those are entirely over. To handle the insane complexity of modern centralized compute architectures, your engineering teams must define logical and physical models in a single unified language right from day one.
This unlocks a multi-agent automated R&D framework. Basically, it executes continuous loops, running these extreme corner case stress tests via cloud-based X-in-the-loop or XIL simulation. By generating massive mountains of synthetic data, you can validate your autonomous driving algorithms across billions of virtual miles. To put that in perspective, that's a volume of testing that would take human drivers thousands of years to complete, and you do it before a single physical prototype even exists. Honestly, it's the only way to meet strict ISO functional safety standards at the absolutely wild speed the modern market demands.
Now, when you couple that R&D with management, your whole enterprise governance shifts. You move from relying on subjective human experience to pure algorithmic execution, using data lakes and operations research algorithms for predictive strategy. Instead of those clunky, siloed ERP and MES systems, we're talking about a composable microservices architecture. Just imagine your management system automatically running Monte Carlo simulations in the background, instantly optimizing your global capacity based on real-time geopolitical supply shocks. That is the sheer power of an IM4 enterprise brain.
Moving on to Section 2, Physical Realization, the ecosystem muscle. This is where we completely tear down and rebuild production and equipment architectures.
The most crucial takeaway here? The total extinction of the rigid conveyor belt. It's being replaced by dynamic, hyper-flexible island assembly that's built from mass personalization. Because let's face it, when the market demands highly customized vehicles delivered at massive scale, rigid sequential lines just become a massive bottleneck. Island assembly completely decouples the process. It routes automated guided vehicles, AGVs, dynamically based entirely on real-time station availability and specific custom build requirements.
Out on the production floor, insanely complex processes like gigacasting now rely on 5G URLLC, that's ultra-reliable low-latency communication. We're talking sub-second digital twin synchronization that dynamically compensates for process variance in real time. By utilizing edge compute machine learning models, the system monitors melt temperatures and mold cooling rates at the millisecond level, automatically adjusting to guarantee yield stability for these massive thin-walled structural parts. Plus, quality inspection jumps to 100% automated coverage using deep convolutional neural networks. No more human error. At the exact same time, passive machines are being elevated into embodied intelligent agents. We're talking robots equipped with their own edge compute brains that actually leverage swarm intelligence to knock out over 70% of critical tasks. So, instead of a welding robot just blindly following some pre-taught, rigid trajectory, it's equipped with laser tracking and force sensors. It dynamically adjusts its spatial posture and welding parameters in real time, actively compensating for geometric tolerances on the fly. It's literally plug-and-play cognitive manufacturing hardware.
All right, let's step into Section 3, Value Network, the nervous system. This is what links our hardware and software supply chains together. For engineering leadership, the mandate is clear. Abandon those linear, super vulnerable, just-in-time models. You've got to pivot to a highly resilient, multi-agent ecosystem driven by graph theory algorithms. I mean, recent geopolitical and climatic volatility have proven beyond a doubt that efficiency without resilience is a total liability. You absolutely must build just-in-case capability directly into the architecture itself.
In the hardware space, this symbiotic ecosystem relies on low-power, wide-area networks and AI predictive analytics. It autonomously matches your global hardware supply to real-time manufacturing demands. Let's say a major port suddenly gets congested. The supply chain's digital twin recalculates the entire topology in milliseconds. It instantly reroutes critical components, like high-end chips or battery packs, effectively absorbing the shock way before it ever hits your assembly line.
And over on the software side, managing a secure software bill of materials, or SBOM, through privacy-enhancing technologies is literally the only way you can deliver secure, thousand-faces autonomous OTA, over-the-air updates. As lines of code just explode exponentially, you need automated parsing tools to manage dependency trees and vulnerability disclosures. We are even seeing federated learning step in, allowing OEMs and suppliers to jointly train predictive models without ever exposing their proprietary source code. It's a game changer.
Which brings us to Section 4, Market and Sustainability, the ultimate impact. This is where we looked at the real-world thermodynamic and consumer results of all this architecture.
Let's pivot entirely to the consumer experience for a second. In this new paradigm, the traditional value chain completely flips. The insanely rich telemetry data coming off vehicles out in the market, that actually becomes the starting point. It instantly feeds back into R&D to continuously close the loop. Every single battery charge cycle, every tiny chassis vibration profile captured from a user, it all flows straight into your data lake. Engineers can then push OTA updates that proactively fix issues before the driver even realizes there's a problem. You're shifting the entire service model from reactive repair to pure predictive maintenance.
And of course, deep decarbonization is baked right into the genetic code of this ecosystem. It relies heavily on thermal cascading and closed-loop material recycling to hit those macro sustainability targets. For example, by utilizing waste heat recovery systems in paint shops or directly physically recycling solid-state batteries, you are creating a true, undeniable cradle-to-cradle engineering loop. All of this ladders up to a massive quantifiable mandate, a greater than 60% reduction in full life cycle carbon footprint by 2040 compared to 2024 baselines. And listen closely, that is full life cycle. We are talking Scope 3 emissions here. You can't just slap some solar panels on your factory and call it a day. You have to architect a fully carbon-accountable supply chain, utilizing PLM systems and blockchain verification to guarantee absolute auditability.
And the timeline? It's incredibly aggressive. It demands the entire industry achieve carbon peaking ahead of national targets by 2028. It also requires rigorous Scope 3 lifecycle tracking to hit those 2040 reduction goals. By 2040, new passenger car carbon intensity must drop by 60%, and heavy-duty 49-ton trucks must drop by 41%. These aren't just suggestions. These are hard engineering targets, and they require immediate action in your system design phases right now, today.
Finally, Section 5, Synthesis and Strategy, the path forward. We've meticulously drilled down into all four MES layers, the brain, muscle, nervous system, and impact. Let's pull it all together into some actionable strategic imperatives for your teams.
To truly weaponize your core data assets, you absolutely must eradicate functional silos. You have to architect open, cross-industry ecosystems and relentlessly invest in digital talent and systems architects. A mechanical engineer today, they need to understand data ontology. A software engineer, they better understand hardware constraints. You are no longer just building cars, my friends. You are cultivating self-sensing, self-optimizing, intelligent mobility organisms.
Because make no mistake, the transition to IM4 isn't just a neat little operational upgrade. It is an extinction-level event for linear manufacturing models. Those who cling to siloed data and rigid assembly lines, they will be mathematically eliminated by 2040. So, I'll leave you, the automotive engineering leaders of today, with this one critical question. Is your engineering architecture truly prepared for self-evolution? Thank you for joining me for this explainer. Take these frameworks, bring them back to your teams, and let's go build the actual future of mobility.